This is IPS Podcast 1.2. This is Unit 1, Podcast number 2. We're going to talk more about the nature of science today, some of the finer points of the scientific method. Let's start off by reviewing the scientific method. The scientific method starts with a question. You can do a little bit of research, and then you can predict what that question will result in, and that's your hypothesis, a research prediction. You can test the hypothesis by conducting an experiment that usually starts with figuring out your constants, maybe figuring out a control, determining your independent variable, and then seeing how the dependent variable changes as you change the independent variable. Next, and finally, you're going to observe your data. You're going to observe your measurements. You're going to analyze the result and see if the question gets answered. So that leads us into the mystery tube of science that I showed you in class last week. The mystery tube of science is a bunch of little experiments. You pull on one string and one of these spherical objects moves. And so your independent variable is what you're pulling, and the dependent variable is what happens. But you can't really figure out what's occurring by just one experiment. You have to really play around with it and pull on a lot of those spherical objects. So let's say, for instance, my tube of science looks like this, with the green spherical object out and the other three in. And let's say I give a pull to the orange object. And this is what happens. So I have one experiment done, and you may have said, well, my hypothesis is that the green one's going to come in and the orange one will go out and the purple and the yellow won't change a bit. But that's not going to explain what's inside of that tube. So we got to keep pulling on things and pulling on things and pulling on things and figuring out what's the connection between them. So you might get to the point where you might want to try something outside of just pulling one, and you might do this. Okay, so let's try this experiment where we have three of these spherical objects sitting out there and one small yellow one that is in. Now, if you haven't seen this before, but you've been working on other experiments, you could probably infer, that's a new word, but you could infer that if you pull out the yellow one, the other three will go in. An inference is kind of taking what we already know and just kind of applying it to future events. So when you pull the yellow, this is what happens. And you probably start to have this idea of what's going on inside of there. Now, since we can't open it up, we'll never actually see what's inside. So the best thing you can do is form a theory. And a theory is just a way of explaining how something works using experiments and going over and going through the scientific method, cycling over and over and over again. So a theory doesn't come from just one experiment. It comes from 10, maybe 100, maybe 1,000 experiments. And so the more experimenting you do, the stronger the theory is. Now, a theory is different from a law because a law tells what's going to happen, but doesn't say how. So we can always, we say the law. This is the law of the tube of science, that when you pull on one ball, spherical object, the others will move. That would be a law, but it doesn't explain how. It just explains the what. The other thing you got to consider is that some scientists have bias, and you might have bias as well. Your favorite color might be green, and so you might actually change your perception, or you might be prejudiced in some way towards the green ball. So you might always say, well, whenever I pull the yellow one, the green one always moves, but that's not always true. So here are these terms. A theory is a way to explain how a process works based off of a hypothesis that's been tested over and over and over and over and over and over and over. An inference, or to infer, is the process of coming up with a logical conclusion based on known premises, like the pulling one ball and seeing the rest of them move. A bias is any inclination or prejudice for or against a set of data, and then a law is a declaration of a natural process that occurs all of the time, yet doesn't really explain how it happens. Okay, you probably know this person. This is Albert Einstein. And you've also been made aware of the law of gravity. The law of gravity is just that law that says that things fall to the ground. But we don't really know why. And Albert Einstein worked on the why. And his theory, called the theory of relativity, works on how gravity works. Now, a lot of people know that gravity just works, but not everybody knows how it works. And the how is answered with a theory. Not a law, but a theory. So law of gravity, that's pretty easy. The theory of gravity, the theory of relativity, that's really complex. And so it takes a lot of experimenting and a lot of hypothesizing in order to understand how a theory works. But that doesn't make theories less useful. In fact, theories are a lot more useful because we can try to figure out how these things work, and once we figure out the how, we can apply that to all other sorts of instances and examples. All right, next we have a couple questions about data. How much data is enough, and what type of data is the right data? First of all, when we measure data, that's one of the things we're going to actually talk a lot about, is measurement. Measurement with a meter stick or measurement with a stopwatch, and we'll spend a good chunk of time making measurements. It's really important. One of the things that when we make measurements, we want to make sure that we have enough measurements to get an accurate data set. And so one of the things we want to talk about is sample size. If you just do an experiment once, and we just kind of saw this with the mystery tube of science. If we just take one experiment and try to explain and try to come up with a theory, well, it's kind of hard. You need a lot of experiments, and you need a very large sample size, or at least a moderate sample size, in order to get accurate data. So what does it mean to be accurate? Well, actually, we have two terms we want to talk about, and those are accuracy and precision. They both seem kind of interchangeable, but there's a significant difference in them. Accuracy, and the best way, I guess, to explain it is using these targets. We're doing a little target practice here. So accuracy means you're close to the target. So we have a target number, and if we are shooting pellets or BB guns, accuracy means you're close to the target. Okay? Precision means that your points are actually very close to each other. So they're not necessarily close to the target, but they're close to each other. Alright? So, to not be accurate would be away from the target, and to not be precise would mean you're all over the place. Okay, but to be both, to be accurate and precise, you would be close to the target and you would be close to each other. That is the difference. That is accuracy, and that is also precision. So you can be accurate without being precise, and you can be precise without being accurate. Our goal is to be both. Finally, we want to talk about taking measurements and taking this quantitative data with a N. A lot of our data is going to be quantitative. We're going to need to measure it. So here I have a meter stick. And remember, your power towers are supposed to get up to 60 centimeters. And so if my power tower is up to about right here, okay, that's at 62 centimeters. But I wouldn't write down 62 because look at, I've got these little bitty lines here, 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 here. I've got these tenths of a centimeter. So I can actually measure to the nearest tenth of a centimeter. So instead of saying 62, I'm going to say 62.0 centimeters because my meter stick is as accurate to the tenth of a centimeter. So if I have another tower that comes up to here and it's 62 and a little bit more, we can actually say it's 62.2 centimeters. So we're always going to measure to the nearest point as our precision allows. This is all about precision. Okay, so we want to be precise in our measurements. So we're going to measure to the nearest tenth of a centimeter here, but in other like say volume, other measurements, we will have to look at our measuring device to figure out how precise we can be. All right, that's it for podcast 1.2. Have a good night.